Okay guys, so here obviously is a second video covering some other essential concepts that we've been trying to learn in AP Stats. So, if we look at this problem here, now this again exemplifies how evil and tricky these problems can be. Sometimes they can even trick me initially, and I have to put in a little extra thought. So, anyways, let's get right down to it. Normally, notice what they're saying here, excuse me, that we're looking at collegiate baseball pitchers. It's normally distributed, so what's the first thing we're going to do is we're going to do a nice sketch, right? And we know that its mean is 86 miles per hour. That's how fast they can throw, with a standard deviation of 4 miles per hour. Okay? Suppose further that Major League scouts will only consider pitching prospects who can throw at least 90. So they're saying, okay, the average is 86, but we're going to be right here at 90. And all we're going to do is look at whoever can throw 90 or higher. Okay? On top of that, we're now asked, here's the question, what percent of pitching prospects who are considered, that means we're only looking here at the 90 or higher, can throw over 95. So now we have to look out here where 95 is, figure out what that little percentage is out of all the 90 plus mile per hour pitchers. Okay? Now guys, this is called a conditional probability, which we will do more of starting in January, okay? Because this is one of the last units I like to cover, and we're going to go through at least most of the common ins and outs of conditional kind of probability and binomial probability, things like that. But anyways, I digress. Let's focus on this problem here. So guys, here's what I would expect you would have done. You knew to do inverse norm. I misspoke there, guys. Second vars, right? That gives you the normal CDF function. Remember, we never picked normal PDF. You would have put in 95 for the lower end. Remember my little trick here? For infinity, just put in at least 5 or 6 nines in there. So we're going from 95 to 99999. We know our mean is 86, standard deviation 4. What we're finding initially right here is the percent of pitchers that can pitch 95 or higher. Then we're going to do normal CDF again. And this time we're going to do it with 90. So instead of 95, we're going to do 90 up to 99,999. Same mean and standard deviation, right? And that's going to find us the probability of this right here that I'm showing in green. All those greater than 90. And so we want to know what percent 95 is out of the 90. So we're going to take our answer here. That's the percent. About 1% can pitch 95 or higher. A total of about 16% can pitch 90 or higher. So what is 95 out of that 90 mile per hour pitchers? It's about 7 to 8%. So we're going to divide to figure out what percent of the 95s are part of the 90s. And that's called a conditional probability, guys. And there it is. The answer, the correct answer was B. Okay, correct answer again was B. Now, 21, guys, I don't even think we need a calculator on. Notice they told us that our initial hypothesis is we're assuming the average is 75. The mean is 75. Notice over here we're suspecting it's greater than 75. So we have a single-sided test, or single-tailed test as we say. Our sample gave us a mean of 76.9 with a corresponding t-score of 2.23 and a p-value of 0.0175. Notice that this p-value, guys, is pretty small. It's less than 2%, a little over 1%, which by far is less than 0.05, right? So 0.0175 is definitely less than 5%. Remember, this is our typical alpha or threshold value, right? So we already know, hopefully, that we are going to reject H naught, and we do have sufficient evidence that mu is greater than 75, right? Because remember, the p-value is assuming that it was 75. Well, if it's 75, that only happens about 1 to 2% of the time. Hence, logically, it must be more than 75. And that's the logic of these hypothesis kind of testing. Now, let's look at our answers. Now, guys, notice the trick again. Now, they don't always do this trick, but I'm focusing on this trick because I want to make sure you don't fall for it. You have to read the question carefully, guys. Notice they want to know what is not reasonable. What is not a reasonable conclusion. So therefore, everything that's valid, we're going to eliminate, right? We want to know which answer is the worst answer, bottom line. So if we look at A here, it says, if the null hypothesis is true, the probability of attaining a sample mean is extreme as we got there is only, that's the basis of testing. That one's actually true. That's why we're going to remember. We want which one is the worst and not true. That is true. That's what we normally do. That's what I taught you, right? B, in all samples using the same sample size, the same sampling technique, the null hypothesis will be wrong 1.75% of the time. Guys, I hope you agree that answer is really weird. It doesn't make sense. It's not what I taught you. So I'm considering answering B. Let's look at C. At a significance level of 5%, that's our normal alpha, there is sufficient evidence to reject the null. Bingo! Since that's true, we eliminate it, right? Because we want to know what is not true, the worst answer, right? D, if the population standard deviation of sigma had been known, then a z-score would have been done, and this 2.23, which we got here as a t-score now, would have resulted in a smaller p-value. Now, guys, this one let's talk about last, but that's actually a true or valid answer. Let me explain here shortly. Let's look at E. If the alternative hypothesis had been two-sided, remember ours was, we knew we were suspecting greater than, but what we would have done, I hope you understand, is double our p-value. So again, if we know, we are doing here, we know that this is 0.0175% chance of happening. But if it was double-sided, we'd have to include here another 0.10175. So you double it. So that one is true. So the key thing about this question, guys, know that A, C, and E are definitely true statements that you ought to hopefully comprehend. Now let's talk about D briefly, guys. Let's talk about D, okay? I've never taught you this before, or actually I mentioned it but never really taught it, right? So know that if this is a Z, or normal standardized curve, a T curve, guys, the only difference is it's still symmetric and almost normal. It's just a little bit more data in our tail, so to speak. It incorporates a bigger, let's call it, room for error or fudge factor. That's really the significant difference between a T and a Z. So if we got a T of 2.23, that means out here and right here, or in our case actually right here, remember it was a single-sided test, that was our 0.0175 p-value, right? Well, with a Z, we have less area here. So a 2.23 would give us a smaller amount because inherently in a Z, it's smaller in the tails, okay? More data is towards the middle, towards the mean here, in other words, okay? And so therefore, logically, if you understand what I'm saying is this p-value for the same score, 2.23, is definitely going to be a smaller amount, percentage, or p-value. Okay, so what did you hopefully understand is a T has more, higher amount of percentage. Not like a huge amount, but just a little bit tinier, smaller amount more in the tails. So Z will have smaller amount in the tails. Okay, let's get to the last question. This one will go pretty fast, guys. So on 23, so again, the answer, guys, is D actually is a true statement. Try to understand that as best you can. But B, guys, just read it again. It doesn't even make sense. It's just a convoluted, stupid answer. That's why B is the worst answer. That doesn't make any sense. Okay, let's go to 23. Nice and quick, guys. Here's the logic. If they give you a table like this, these are what we call the probability or frequencies for each of these data pieces, right? These numbers, 0, 1, 2, 3, 4, 5, is how many cars they're selling in a given week, these hybrid cars, right? So here's the logic. Zero cars are sold 32% of the time. One car a week is sold 28% of the time. Two of these hybrids are sold 15% of the time. Three hybrids are sold 11% of the time. Four hybrids are sold 8% of the time. And finally, 5 hybrids are sold 6% of the time. So basically, if I take each value times their percentage and add them together, I get what we call a weighted average. And that weighted average is actually the mean of our probability distribution here. So, long story short, you would take the calculator and go 0 times 0.32 plus 1 times 0.28 plus 2 times right? And you would get 1.53 average cars sold in a given week. So what's the real catch then? Is you have to remember, we have to factor in, they want the actual profit. Well, what is the profit? Every car costs the dealer $21,000. They sell it for $24,500. So that difference is $3,500. So therefore, every hybrid car they sell, theoretically, they're making $3,500 profit, right? So we have to take the average amount of cars sold times our profit for each car, which is $53.55. And so the correct answer would have been C. Okay? Now, here is another clever way I hope you would understand. I could have done stat edit, put in 0 through 5, put in their corresponding frequencies, gone to one variable stats. That would be stat calc. Guys, all this on the calculator, please practice, right? And list 1, of course, is our data. List 2 is our frequency list. And we would calculate. And that would be a clever way of getting the 1.53. And then, of course, we would still take that 1.53 times the profit per hybrid and get 53.55. So, guys, I hope you go through these problems one by one in detail. Again, I'll keep reminding you the underlining concepts here, okay, that we must master between now and the AP Stats exam. See you in class.